Hello and good afternoon friends, welcome to the CEC EduSet live lecture. Dear friends, with our ongoing series on thermodynamics, today we would be talking on calculation of entropy change, and for this very discussion on the topic we have once again with us in our studios Dr. Shashank Deep. Dr. Shashank Deep is Associate Professor in IIT. So let's welcome our guest Dr. Shashank Deep and let's try to understand more and more about the topic calculation of entropy change. Hello sir, welcome to the EduSet lecture.
Thank you, Geetika. A very good afternoon, students. This module is basically we are going to focus on how to calculate entropy change during various processes. I have already told you in previous modules that entropy is a very important thermodynamic parameter. Basically, if you want to know about any process, whether that is going to take place or not, entropy is the parameter which can tell you about that. We all know that during a spontaneous change, entropy of system plus surrounding increases. So, a process is spontaneous only when entropy of system plus surrounding, which is called total entropy, increases. Entropy is related to randomness. So, basically when we say that entropy is increasing, what we mean is randomness of universe is increasing during a spontaneous process. It is also related to multiplicity, and during a process the multiplicity maximizes. So, it is very important to understand entropy. In the last lecture, I told you about how this entropy term came. We needed a parameter which is a state function, and since heat is not a state function, it is a path function. So, we come up with a thermodynamic term which is a state function and can measure disorderness. So, in this lecture we are going to discuss how to calculate entropy change for various processes. I would like to start with recap, and this is the definition. Your ds is your dq reversible by t. So, entropy change, thermodynamic definition of entropy change is that a differential of S equal to dq reversible by t. You must focus on this term reversible. What does that mean is, if that process is carried out in reversible manner, the heat change is given by dq reversible, and that divided by T gives you change in entropy. So, you must focus on this, that this is dq reversible. So, it is not simply dq by t. If it is dq by t, it is not going to be a state function, and that is why it is defined as ds is defined as dq reversible by t. So, ds system is dq system reversible by t system, whereas ds surrounding is equal to dq surrounding by t surrounding. And since heat lost by the system is equal to heat gained by the surrounding, and so dq surrounding is equal to minus dq system, and so you can write ds surrounding is equal to minus dq system by ds surrounding by t surrounding. Entropy change, we know how to calculate entropy change in a system, and we also know how to calculate entropy change for a surrounding, and the sum of this delta S system plus delta S surrounding is going to give you total change in entropy during a particular process. Now, how to calculate entropy changes in a reversible process? For that, you must remember these formulas which we have derived during previous lecture, that is dq reversible is equal to du minus dw. This is from first law of thermodynamics, where du is change in internal energy and dw is the work done. So, if the process is reversible, you can simply write dw is equal to minus p dv. So, minus dw is plus p dv. So, dq reversible is equal to du plus p dv. So, this is the first formula which we are going to use when we calculate entropy change for a reversible process. dq reversible can be also calculated by using enthalpy. So, we know that U is equal to H minus PV. So, du can be shown as dH minus PdV minus VdP, dH minus PdV minus VdP, and if you add du this dw, we have PdV term, PdV cancels out, PdV cancels out, and we are left with dH minus VdP. So, this is the second equation which we are going to use for calculation of dq reversible. If we take a constant pressure process, VdP terms becomes 0, and you can have dq reversible is equal to dH. So, dq reversible at constant P is equal to dH. So, these are the three very important terms which gives you dq reversible. Now, we know how to calculate dq reversible. We can now go and calculate what is the entropy change in the reversible process. First equation, let us focus on the first equation, dq reversible is equal to du minus pdv. So, what is du? Du, as I told you in previous lecture, that internal energy can be written in terms of function of volume and temperature. This is quite convenient to express U in terms of volume and temperature, because the two terms which we get in du is a very well known term. So, del U by del T at constant V is known as heat capacity at constant volume, whereas del U by del V at constant T is called internal pressure. This tells you about the your intermolecular attraction or repulsion between two molecules of a gas or two molecules of a system. And we know that del U by del V at constant T is equal to 0 for an ideal gas, and this is your simply heat capacity at constant volume. So, differential of U is given by heat capacity multiplied by dt plus internal pressure multiplied by dV term. Again, we will like to just give a relook at what is the enthalpy. Enthalpy is generally expressed in terms of your function of temperature and pressure. So, del dH is equal to del H by del T at constant V dt plus del H by del P at constant T dP, and this is your heat so del H by del T at constant P, this is your heat capacity at constant pressure. Del H by del P at constant T is isothermal Joule-Thomson coefficient. Again, H is generally written in terms of function of P and T, and del H by del T at constant P is your heat capacity at constant pressure, where del H by del P at constant T is your isothermal Joule-Thomson coefficient. Now, you have two different terms which you come across when you are trying to calculate del U and del H. First term is your del U by del V at constant T, which is known as internal pressure, and internal pressure can be calculated using thermodynamic equation of a state, and the equation which is generally used is T del P by del T at constant V is equal to del U by del V at constant T plus P. So, internal pressure is given by this equation. So, del u by del v at constant t is equal to T del p by del t at constant v minus p. Similarly, isothermal Joule-Thomson coefficient can also be calculated using thermodynamic equation of a state, which is given here. T del v by del t at constant p is equal to v minus del h by del p at constant t, and del h by del p at constant t is equal to v minus t del v by del t at constant v. So, these are the two equations which can be used to calculate your du and dh. Now, we have du, dh, and you know how to calculate work done. So, you can calculate dq reversible, and from the dq reversible we can calculate what is the change in entropy if we change temperature and volume. So, for calculation of change in entropy with temperature and volume, we will use a function, use a parameter which is a function of temperature and volume, and generally we denote u as a function of temperature and volume. So, dq, the relationship which we are going to use is dq is equal to du minus dw, and just I showed you that du can be written in terms of heat capacity and internal pressure. So, dq reversible is nothing but del u by del t at constant v dt plus del u by del v at constant t dv, and minus dw is equal to plus p dv, that we can only write when it is a reversible process. So, dw is p dv minus p dv only when the process is reversible, and since we are calculating dq for a reversible process, so we can always write d minus dw is equal to plus p dv. So, dq reversible is simply del u by del t at constant v dt plus, if you combine these two equations, we can get del u by del v at constant t plus p dv, and so we can calculate dq reversible by t, which is nothing but ds, and that is simply 1 by t of this quantity and 1 by t of this quantity. So, this is the way to calculate entropy as a function of temperature and volume. So, dq reversible by t is given by this equation 1 by t del u by del t at constant v dt plus 1 by t, and then this summation of two pressure term, internal pressure plus pressure multiplied by dv. And we know from the thermodynamic equation of a state that del u by del v at constant t plus p is equal to T del p by del t at constant v. So, we can replace this whole quantity by T del p by del t at constant v. Now, you see T cancels out. So, you are left with this whole equation becomes equal to del p by del t at constant v, and so we can write ds is equal to 1 by t del u by del t at constant v dt plus del p by del t at constant v dv, and this is equal to Cv dt by t plus del p by del t at constant v dv. So, now we have a general equation. This is applicable to any process or any system which goes from a particular state to another state. So, only thing here is that we are taking as a reversible way, but delta S can only be calculated if we go through a reversible path. So, this is a general equation that ds is equal to Cv dt by t plus del p by del t at constant v dv. But suppose in a process temperature and pressure is changing. In that case, how we can calculate entropy. Similar the way we did in the last few slides, we are going to do same thing here. It's simple that when we are going to calculate dq, we are going to use your enthalpy term, because enthalpy is generally written as function of pressure and temperature. So, instead of using du for calculation of dq, here we are going to use dh for calculation of dq. So, the equation is dq is equal to dh minus v dp, dh minus v dp. Now, if we calculate dq reversible, again we are trying to calculate reversible, we can simply write del h by del t at constant p dt, this is for dh, and plus del h by del p at constant t dp. So, this is for dh, since we write h as a function of p and t. So, we can just replace dh by these two terms and we have minus v dp. So, you see these two terms have dp terms. So, these two can be combined, what you get is del h by del p at constant t minus v into dp. So, this is the subtraction or difference between two volume terms. One is isothermal Joule-Thomson coefficient and this is simple volume, and when you calculate dq by t, you just divide this whole term by t. Now, we know how to calculate del h by del p at constant t, which is isothermal Joule-Thomson coefficient, and that generally we calculate using thermodynamic equation of a state, which is your del h by del p at constant t is equal to minus t del v by del t at constant p plus v. And so, the previous equation, previous equation becomes ds is equal to 1 by t del h by del t at constant p dt minus del v by del t at constant p dp. So, this is simply Cp dt by t minus del v by del t at constant p dp. So, if we change pressure and temperature, or in a process pressure and temperature gets changed, we can calculate delta S using this equation. This is a general equation which is applicable to any kind of gases, whether that is a perfect gas or van der Waals gas or any kind of gas obeying any kind of equation. We can calculate your entropy change ds. So, now let us think about how to calculate entropy changes in a reversible process. So, first we will discuss about reversible process and then we can go and see how to calculate entropy in a irreversible process. One of the most important process which we come across is phase change. So, for example, melting of ice, boiling of water, conversion of one form of carbon to another form of carbon, like carbon graphite to carbon diamond, these are called your phase changes. Phase change is always a reversible process and they take place at constant temperature and pressure. They take place at constant temperature and pressure. So, temperature does not change till liquid converts totally into vapor. In that case, again ds is given by dq by t, ds is given by dq reversible by t, and since the process takes place at constant pressure, we can simply write dqp at constant pressure divided by t, and that is simply equal to dh by t. So, if we know the enthalpy of the process, we just divide by t and we can get delta S of the system, delta S of the system. So, one thing you must remember that this is a reversible process. So, the heat which is evolved is simply divided by T, and heat evolved is here at constant pressure. So, this is equal to dH, and if you know the enthalpy change, you can simply divide by the temperature of phase change and then you can get what is the delta S for the system. How to calculate delta S surrounding? Delta S surrounding is simply, we know that this is dq surrounding by T, and dq surrounding can be expressed in terms of system, because we know that heat lost by surrounding is heat gained by the system. So, we can simply write minus dq if we want to express in terms of system, and since we are talking about phase change, which is a reversible process, we can simply write dq reversible by T, and which is minus dH by T. So, delta S surrounding is minus delta H by T. So, delta S surrounding is nothing but minus of delta S system, and so delta S total is basically 0. So, for a reversible process, total entropy change is going to be 0. Delta H vaporization can be calculated using Troughton's rule, which tells you that delta H of vaporization is equal to Tb, which is boiling temperature, multiplied by 85 joule per Kelvin per mole. So, if you know delta H, you can always calculate delta S. Delta S system and delta S surrounding can be calculated using delta H of the process. Now, let us take an example. If suppose we have to find out delta S for melting of 5 gram of ice at 0 degree Celsius and 1 atmosphere. Just I told you delta S is simply equal to delta H by T, and delta H is your heat of fusion. You just see that it is given in calorie per gram. So, you need to multiply by the weight of the ice. So, 79.7 multiplied by 5 and divided by temperature, which is 0 degree Celsius, and in Kelvin it is equal to 273, and so we get 1.46 cal per Kelvin. And if you express this in terms of delta S, this is simply multiplied by 4.18, and you can get delta S in joule per Kelvin. So, it is quite simple to calculate delta S system when the process is reversible. For example, when there is a phase change. So, delta S system in this case, in particular this case, is 6.1 joule per Kelvin, and then you can think of how to calculate delta S surrounding, because delta S system plus delta S surrounding is going to be 0 for a reversible process. So, delta S surrounding is nothing but minus 6.1 joule per Kelvin. Now, suppose there is a heating or cooling process at constant volume, then in that case what will be delta S? We know that heating and cooling can be carried out reversibly, and so delta, this is the formula which already we derived, that ds system is equal to Cv dt by T plus del P by del T at constant V dV. We are carrying out heating or cooling at constant volume. So, constant volume means this term is 0, we are only left with Cv dt by T. So, delta S system is Cv dt by T. So, delta S system, if you integrate this, you can get delta S system, and delta S system is Cv multiplied by log Tf by Ti, which is Tf is your final temperature and Ti is your initial temperature. So, delta S system is dependent on two terms, one is Cv, heat capacity, and your temperature. Now, suppose heating and cooling is not taking place at constant volume, but it is taking place at constant pressure. In that case, how to calculate delta S? Again, we remember the second equation which we derive for your delta S, a ds system is Cp dt by T minus del V by del T at constant P dP. So, since the process is taking place at constant pressure, so this term is going to be 0, and thus ds system can be written as Cp dt by T. So, now see the difference between when we are doing heating and cooling process at a constant volume, then your ds system is equal to Cv dt by T. Now, we are doing heating and cooling at constant pressure, and equation changes, ds system now becomes Cp dt by T. And so, delta S system is Cp log Tf by Ti. Now, does this equation make sense? We just derived that delta S system is equal to Cv log Tf by Ti. So, if Tf increases, your final temperature increases, then entropy should increase. This equation tells you that if temperature increases, your delta S will increase, and that is quite understandable, since if I increase the temperature, disorder is going to increase. It is quite logical that if I increase the temperature of a gas, disorder of gas will increase. And so, delta S system must increase, and this is quite clear from this equation also, that if we are going to increase the temperature, delta S is going to increase, and the way it increases in exponential manner. So, if I plot delta S by versus Tf by Ti, there will be an exponential curve, and you can get the curve like this, the lower one. Now, on what other things delta S will depend? Delta S will also depend on heat capacity. So, if we increase suppose temperature from 300 to 400 Kelvin, every substance does not going to have same entropy change. It will depend on your heat capacity of that substance. For example, if substance has higher heat capacity, your change in delta S will be higher. If substance has lower heat capacity, the delta S will be low, delta S, and this is quite clear from this curve. You see, this is the low heat capacity and this is high heat capacity. So, delta S change is higher when heat capacity is high. We can just think of in just opposite way, that if delta S is higher, means that heat capacity of that substance must be higher. So, suppose we increase the temperature from 300 to 400 Kelvin, and we see entropy change for a particular substance is greater than the another substance, for example B. So, if delta S for A is greater than delta S of B, it means A must have higher heat capacity than B. Now, let us think about how to solve this problem. Find delta S for the water when 100 gram of water is reversibly heated from 25 degrees Celsius to 50 degrees Celsius at 1 atmosphere. So, Cp of water is delta Cp of water is 1 cal per gram per Kelvin. In that case, delta S can be calculated using this equation Cp log T2 by T1. So, delta S is equal to 100 log 323 by 298 and delta S is 8 cal per Kelvin. So, this is the way you can calculate delta S when there is a heating or cooling. Thank you. So, we are looking at how to calculate entropy change for various processes. We just discussed how to calculate the entropy change for a reversible process. and the equation which we derived is these two. These are very general equations, that ds is equal to Cv dt by T plus del P by del T at constant V dV. The second equation is your ds is equal to Cp dt by T minus del V by del T at constant P dP. The first equation is generally used when there is change in volume and temperature. So, you can see here S is function of temperature and volume, while the second equation is used when we have change in pressure and temperature, since here S is a function of temperature and pressure. When there is a heating and cooling, these two terms goes to 0 when it happens at constant volume or constant pressure, and so we are left with only Cv. ds is equal to Cv dt by T when temperature when volume is constant, and ds is equal to Cp dt by T when pressure is constant. Now, let us discuss how to calculate delta S for an ideal gas. Suppose a process is reversible and process is isothermal. Reversible means your dW is equal to minus PdV. Isothermal is your isothermal ideal gas. You must remember this, we are calculating for ideal gas. We just showed that ds is equal to this equation, Cv dt by T plus del P by del T at constant V dV. Now, delta S system, since this is the isothermal process, so Cv dt by T is equal to 0. So, we are simply left with ds system is equal to del P by del T at constant V dV. Since this is a isothermal process, so we have taken this equal to 0. Now, how to calculate this? Since this is an ideal gas, del P by del T at constant V can be calculated using PV is equal to nRT. When we calculate del P by del T at constant V, this is simply equal to nR by V. So, ds system is equal to nR by V dV, and if you integrate this, we can calculate delta S of the system, and that is equal to nR log V2 by V1, and delta S surrounding is equal to minus nR log V2 by V1. This is simply because for a reversible process, delta S system plus delta S surrounding is equal to 0. Now, you see here that delta S system is equal to nR log V2 by V1. It is quite obvious. If we increase the volume of the system, your randomness is going to increase or disorder is going to increase, and so entropy is supposed to increase, and that is what this equation shows, that if V2 by V1 is greater than 1, then this whole quantity will be positive and you have delta S positive, and so S of the system increases when there is an expansion. Now, suppose that the same isothermal process is carried out in an irreversible manner. In that case, in that case, how we are going to calculate delta S system and delta S surrounding. Now, if suppose that during the irreversible process, same thing is happening, that temperature is you see isothermal, so temperature is same. V1, the system is going from V1 to V2, and so you are going to have the same equation, delta S system is dq reversible by T, which is nR log V2 by V1, nR log V2 by V1. How to calculate delta S surrounding? So, if suppose the initial and final state is same, it is not going to matter whether you are going from a reversible pathway or irreversible pathway. When you are calculating entropy, you are just looking at what is the initial state, what is the final state, and then try to go through a reversible path to calculate entropy change. So, if initial and final state is same, it does not matter that whether you go through a irreversible path or reversible path, delta S is going to be same, because since your delta S is a state function. So, again in this case we are getting delta S system is equal to nr log V2 by V1. How to calculate delta S of surrounding? So, delta S surrounding is your dq surrounding by T, and if you write in the terms of system, you can simply write minus dq system by T. So, minus dq system by T. Now, this is isothermal process and you are discussing about ideal gas. For isothermal process, for an ideal gas, delta U is equal to 0. So, minus dq is written as simply equal to minus. So, since du is equal to 0, so dq minus dq is equal to minus dw. So, w by T. So, delta S is simply w by T, and w for irreversible process is P external V2 minus V1 by T. So, from that you can calculate what is delta S surrounding. So, now you see that delta S surrounding is different for a irreversible process. It means delta S surrounding is not a state function. Now, suppose we change the process. Now, we are doing same expansion, but through a adiabatic process in a reversible manner. Since this is adiabatic, so dq system is going to be 0, and we know that delta S ds surrounding is equal to minus dq system by T, and since in adiabatic process dq system is equal to 0, so ds surrounding is 0. It means delta S surrounding is equal to 0. So, this does not matter whether you are going through a reversible pathway or irreversible pathway. Delta S surrounding is going to be 0 if you have an adiabatic process. But suppose we are carrying out this reaction, this process in a reversible manner, then what will be delta S system? Delta S system is simply dq system reversible by T, dq system by T, and since this is an adiabatic process, so dq is equal to 0, and so we have dq system by T is equal to 0. Adiabatic process for an ideal gas, but this now you are carrying out in a reversible manner. If we are carrying out this in a irreversible manner, we have ds system is equal to dq system divided by T, and dq system reversible divided by T, but this is not now equal to dq system by T. So, suppose we carry out the system, so dq system, this is not equal to dq system by T. How do we calculate delta S system in this case is equal to, so delta S system is equal to, we are going to use same equation which we earlier derived for calculation of delta S, that R log Vf by Vi plus Cv log Tf by Ti. Now, you see this is Tf irreversible because now the temperature is going to be different. Then when we try to go adiabatic process in a reversible manner from Vf to Vi. So, delta S system is equal to, and this is R log Vf by Vi is simply equal to minus Cv log Tf in reversible by Ti plus Cv log Tf by Ti. So, delta S system is Cv log Tf by Tf irreversible by Tf reversible. So, since your Tf irreversible is not same as Tf reversible, and so delta S system is not going to be 0. Delta S system is going to be different, and the way we can calculate either by using this equation if you know the final temperature, and or you can calculate delta S by using this, the second equation. For example, here is a one calculation, one problem which you can understand. So, problem is like a sample of 1 mole of monoatomic perfect gas where CV is equal to 1.5 bar initially at 298 K and 10 liter is expanded with the surroundings maintained at 298 K to a final volume of 20 liter. Now, you see here volume is your 10 liter. So, V1 is 10 liter, initial volume is 10 liter, final volume is 20 liter, temperature T1 is 298 K while temperature of surrounding is 298 K. Now, what we need to calculate is what is delta S of the system. Now, the answer will depend on how this expansion is carried out. So, suppose expansion is carried out isothermally and reversibly. In that case, what will be the delta S? So, this was the things which I taken from the last slide, that V1 is 10 liter, V2 is 20 liter and T1 is 298 K. We know this equation. This is only valid for ideal gas, that delta S is equal to CV log T2 by T1 plus R log V2 by V1. This R log V2 by V1 will change if we have a gas other than an ideal gas. So, delta S, since this process is carried out isothermally, so CV log T2 by T1 is equal to 0. So, delta S is simply equal to R log V2 by V1, and we know that V2 is 20, V1 is 10, and so 20 by 10 is equal to 2, so R log 2. And since the process is reversible, delta S surrounding is simply minus delta S of the system, and that is minus R log 2. Now, suppose we carry out this process expansion isothermally against a constant external pressure of 0.5 atmosphere. Again, delta S is given by dq reversible by T is equal to CV log T2 by T1 plus R log V2 by V1. Isothermally means CV log T2 by T1 is equal to, this part is 0. So, delta S is equal to R log V2 by V1, and since it is going from 20 liter to 10 liter, so we can 10 liter to 20 liter, so we can write R log 2. How to calculate delta S surrounding? We know that ds surrounding is equal to, always we can calculate ds surrounding by using this equation. Ds surrounding is equal to dq surrounding by T, and dq surrounding is equal to minus dq of the system divided by T, since heat lost by the surrounding is equal to heat gained by the system. And from the first law of thermodynamics, dq is simply equal to du minus dw by T, and so we can simply write this as minus dw by T, which is ds surrounding is P external dV by T, and delta S surrounding is equal to P external V2 minus V1 by T. So, this is the way to calculate delta S surrounding. It is simply that delta S system will be calculating using this equation always, and delta S surrounding will be calculated using your dq surrounding by T. Now, suppose this time we are going to do expansion adiabatically, not isothermally, adiabatically against a constant external pressure of 0.5 atmosphere. Adiabatic means dq is 0, so ds surrounding is 0. So, any adiabatic process, ds surrounding, delta S surrounding is going to be 0, whether you carry out in a reversible manner or irreversible manner. And but if you want to calculate ds system, first thing you need to calculate the du, final temperature, because you must remember that when we are calculating delta S of the system, we are going to use this equation. We know already what is the value of V1, V2, we know T1, we need to know T2. How to calculate T2? T2 can be calculated using this equation, du is equal to dw. du is equal to dw and since internal pressure is 0 for an ideal gas, du can only be written in terms of Cv dt. So, Cv dt is Cv T2 minus T1, and your dW is minus P external V2 by minus V1. So, from this equation we can calculate what is the T2, because we already know P external, V1, V2 and T1. It is quite easy to calculate T2. Once you know T2, you can calculate delta S, since other parameters is already known. You know V1, V2, you know T1, you know Cv, and so you can calculate delta S of the system, and delta S surrounding is already 0 for any adiabatic process. So, till now we calculated entropy change for an ideal gas. Now, suppose we want to calculate entropy change for a van der Waals gas, or gas which obeys van der Waals gas equation. In that case, how to calculate your delta S of the system and delta S of the surrounding? Again we will go to the general equation, which is ds system is equal to Cv dt by T plus del P by del T at constant V dV. You must remember this thing, that del P by del T at constant V for an ideal gas is equal to Nr by V. But what is the del P by del T at constant V for van der Waals gas? This is equal to simply Nr by V minus Nv. So, for a van der Waals gas, everything remains same. ds system is Cv dt by T plus your, in this derivative, in place of this derivative you have Nr by V minus Nv and into dV. So, this is your equation for a van der Waals gas. Again you see, if just only you do heating or cooling, this term vanishes, and you have delta S system is Cv log T2 by T1. But if volume changes, then at constant temperature this term vanishes and you have delta S system Nr log V2 minus Nv divided by V1 minus Nv. But total equation is integration of this whole thing, delta S system is equal to NCV log T2 by T1 plus Nr log V2 minus Nv by V1 minus Nv. Now, this is a simple sample problem, that what is the delta S for a van der Waals gas when 1 mole of gas undergoes an expansion from 1 liter at 298 K to 10 liter at 373 K, and Cv is given. Simple equation, just we derive that delta S is equal to Cv log T2 by T1 plus R log V2 minus B divided by V1 minus B. This is for van der Waals gas, and this changes to R log V2 by V1 for an ideal gas. If we put all the values, for example, V1 is equal to 1 liter, V2 is 10 liter, B is given here, delta Cv is given here, this is Cv 29 joule per Kelvin per mole, and you can calculate what is the delta S, that is 8 cal per Kelvin. Now, the second question is your how to calculate how to solve this question. A 50 gram mass of copper at a temperature of 393 Kelvin is placed in contact with 100 gram of copper at a temperature of 303 Kelvin in a thermally insulated container. Calculate Q and delta S for the reversible process. Use the value of this for a specific heat of copper. Now, you see there are two blocks of copper, one with a mass 50 gram at high temperature, another with a mass 100 gram at low temperature. So, suppose they are brought in contact, then what will happen, that heat will flow from this block to 100 gram block, and the heat lost by 50 gram copper will be equal to heat gained by 100 gram copper. And what does that mean? That MHCDT for the hot block is equal to MCCDT of the cold block. And from this we can calculate your temperature of the final temperature of the blocks, and that is equal to 333 Kelvin. So, once we know the final temperature, we can calculate entropy change, and entropy change is equal to delta, the sum of entropy change for a hot block plus entropy change of cold block. That is delta S is equal to NH C log, this is the final temperature 333 by 393 plus NC C log 333 by 30. In this block, we can assume that the things are carried out at constant volume, because heating does not change your volume of solid very much. So, this process are carried out at constant volume. So, you have only temperature terms left, and so we can calculate what is the total entropy change for the process. We can calculate. So, till now we are discussing about how to calculate entropy change in a reversible process, but we can calculate entropy change for a irreversible process. Since entropy is not defined for a irreversible process, what we need to do is that we should carry out that irreversible process in several different processes which can be carried out reversibly. For example, suppose we want to calculate delta S for freezing of water below its freezing point. For example, H2O liquid minus 10 degrees Celsius is going to H2O solid minus 10 degrees Celsius. So, this is a irreversible process. This will happen spontaneously, that if we take water at minus 10 degrees Celsius, water will try to solidify. Now, this is a reversible process. How to carry out, how to calculate delta S for the process, and the way we can carry out is, first, since heating and cooling can be done reversibly, so first bring it to 0, and at the melting point this process is reversible, liquid to solid, and then you again decrease the temperature. So, here heating followed by phase change followed by cooling, and now you can calculate what is delta S. Delta S is C liquid log 273 by 263 plus delta H by T plus C ice log 263 by 270. So, this is the way we can calculate entropy change for an irreversible process. What we need to do is we need to combine, need to express this whole process in terms of several different reversible processes. So, till now we are calculating entropy change for processes. What about if you want to know entropy of particular substance? And at this point, third law of thermodynamics comes. It tells you that entropy of each pure substance element in a perfectly crystalline form is 0 at absolute 0. So, you know that entropy is 0 at one temperature, and since you know how to calculate delta T, how to calculate change in temperature, you can calculate the entropy of a substance at different temperature. For example, entropy of a solid can be calculated as S at temperature is equal to S0 plus, so this is at temperature 0, which can be 0 if this is a crystalline substance, and then you just increasing temperature 0 to T Cp dt by T. So, we know how to calculate the temperature delta S when you go from 0 to T temperature, and thus this is how you can calculate entropy of a solid. Entropy of liquid we can start at from the temperature 0, then go to freezing point. Till freezing point your substance is in solid form, so you got this. Then there is a phase change from solid to liquid, del H by Tf, delta S will be equal to, and then delta S for increasing temperature from freezing temperature to T, which will be given by Cp liquid dt by T. So, this is how you can calculate entropy for a liquid, and finally entropy of a gas, and you can start from the temperature 0 at which your substance is in solid form, then you go to freezing temperature. This is your entropy change. At the freezing temperature, when your substance goes to a liquid form, then delta S is equal to delta HF by TF. Now, you increase the temperature to boiling point. Till that point your substance is in liquid form, and you can give your delta SCP liquid dt by T. Now, you are changing liquid to vapor, and in that case delta S is given by delta H vaporization by boiling temperature. And finally, the temperature of the gas. So, from the boiling temperature you are going to temperature of the gas, and at this point your delta S is given by Cp gas dt by T. So, by solving this you can calculate the absolute entropy of a gas, and this is how you calculate entropy change for different processes. You calculate entropy for a particular substance. I hope this will help you whenever you are given a problem to solve. Thank you very much.
With this note, we would like to thank Dr. Shashank Deb, and dear friends, if you want to give a feedback for this particular lecture, then you can mail us at info.cc@nic.in. We would be meeting again very soon. Till then, take care. Goodbye. Thank you, sir. Thank you so very much.
Thank you very much.